Hello and welcome back to another lecture. This one's about probability. You should be fairly familiar with probabilities only because, I don't accuse you of having gambled in the lotto, but because you bump into probabilities all the time. What are the chances of success on something? What are the chances something will come up? What are the chances that you might actually know something more than somebody else has actually misspoken here, being more than 100% in that cartoon. So probabilities are fairly common. Maybe it would be useful first if we define just what we mean by probability. Then we'll get around to different kinds of outcomes, meaning that there's binary versus continuous kinds of distributions, but you'll see in a second. Then we can calculate the distributions of those probabilities. It will be important that we consider whether probabilities are independent or related to each other. That means that we can then get around to talking about conditional probabilities. That means a probability of something depends on another probability. It will also be important to talk about how do you sample to calculate probabilities, because you can sample with and without replacement, putting that jelly bean back in the jar and sampling again to see if you get the same color, for instance. And then we lead to random variables, which is another way of saying you have a large distribution of lots of possibilities within a range, and many possible numbers could come up, essentially forcing it to be completely random when you select one of those numbers. And then that sets us up for the understanding of what is a continuous distribution and histograms, which we'll be using quite a bit in the next lecture, which is about distributions. So what is meant by probability? Let's start off with that. Probability, simply defined in the textbook that we're using, is the proportion of times an outcome would occur if we observed a random process, random sampling of many different separate events. Wikipedia more shortly and less completely says it's the measure of the likeliness that an event will occur. That's leaving out the bit about it needs to be a very large number of times that you allow this random process to occur. Webster's says something sort of in between, a measure of how often a particular event will happen if something is done repeatedly. Again, repeatedly and many times is probably a key there. So, classic examples: tossing a dice, flipping a coin. 1 out of 6 times when you toss a die is singular, it will come up with a 6. Well, that's only true if you do it many times, right? If I asked you to do it once, you only have a 1 out of 6 chance. But if you do it many times, you would find out that that is reliably 1 out of 6. Same thing with tossing a coin. You do it once, you may not get heads, but you do it many times. Eventually, half the time, it would turn out to be that way. 3 out of 5 times, you will find dogs are sleeping if you sampled many dogs. Okay, this is simply true only if you have many numbers, many sampling events. So another way to say that is the law of large numbers. As more observations are collected, the proportion of those occurrences with a particular outcome you're thinking of, heads for example, converges to the true probability of that outcome. That probability P is something we're always trying to estimate. The idea is that you have a larger sample size, you get a better estimate. Okay? So all these probabilities are really assuming that you have sufficient sample sizes. And we'll get around to the effects of inadequate, or relatively smaller anyway, sample sizes, and we look at distributions and the effects of small samples on those distributions. But that's the next chapter, next lecture. Okay, so what kinds of outcomes can we talk about? Different kinds of outcomes. Well, first off, we should think about ones that are mutually exclusive. They cannot both happen. You cannot get both a 6 and a 2 and a 3 on that dice. You cannot get a 1 and a 2, as I'm trying to show here in this example. All right? You cannot have both of them unless there's something really strange with the dice and it stands up on a corner, and then you have to decide which one is 1 or 2. So the probability of a 1 is 1/6. The probability of 2 is also 1/6. The probability of a 1 or 2 is the probability of the 1 and the probability of 2. We're adding these together. So the probability of a 1 or 2 is 2/6, or 1/3 of all the possible sides of that die, right? Okay, so if we have mutually exclusive outcomes, we would figure out what some of these probabilities are of more than one just simply by adding, like I did there. Okay, So this is the additive rule because they're based on the exact same process. You roll the dice and you find out in that one roll what the probabilities of a 1 or a 2 might be, all right, in that one process, that one roll of the die, all right? What about if they're independent processes? We're talking about two processes that are independent. The roll of a die is completely separate of the roll of a second die. Or I toss a coin and I don't really know how it's going to come out if I toss the coin a second time, okay? So it could be two separate events that are going on simultaneously, or the same event repeated again, but the idea being that the outcomes of step number 1, process number 1, are completely separate, independent of the outcomes of process number 2, all right? So that's what we mean by independent probabilities. So the idea, once again, being tossing a die, you get a 1. Probability of that is 1/6. Toss again, and you get a 1. The probability of that is again 1/6, right? That doesn't change. But now how do you figure out the odds of getting a 1 and a 1 again, right? The odds of getting 1 2 times in a row. It's really 1/6 of 1/6, right? The chance of getting 1 is 1/6, and to do it again is 1/6 of those first outcomes. So the probability of 1 and 1 is a multiplication, and it's 1 out of 36 tosses would you get 2 1s in a row. So we're multiplying. This multiplication rule applies to having independent processes, as we often think about in statistics. But it's going to be important that you recognize that sometimes probabilities are additive and sometimes they're multiplicative. And it's important because it would really change the long-term or the eventual probabilities, the calculations that you make, whether you're multiplying or adding, of course. So a simple example. This one's actually in the text we're using. If 91% of people are right-handed, what are the chances that if you walk across campus, 10 randomly selected people will all be right-handed? Well, it's simple. 0.91 times 0.91. You do that 10 times, or 0.91 to the 10th, and you get a 0.389. So almost 40% chance that if you walked across campus and you shook hands with 10 people, they would all be doing that right-handed. Okay? That's a simple multiplicative outcome because each person is independently right or left-handed. Okay, so we can calculate distributions of probabilities by adding these kinds of chances up across lots of different samples. So let's give you a good example of what a probability distribution is. Probability distributions really come from having tallied up lots of possible outcomes among many choices. This is one that I think of fairly often when I think about a probability distribution. We hear about the 1%, right? The people who are making so much money that they're out there on the far upper end on the top 1% of income bracket. In fact, the bars that you see right here in the far right end are stacked up. They're accumulated because we're piling up everybody in the 200 to 250,000 range, and this bar, the last one, is everybody who makes more than 250,000. So actually, the tail goes way, 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 way out to the right hand, and they just stacked them all up because they didn't want to graph this so far out to the right. Okay, notice that every one of these columns here is representing a percentage of households. So with a sufficient sample, like this one from the U.S. Census in 2012, we're looking at the probabilities of people making a certain amount of outcome in a household because it's an adequate sample, and we can see that it's pretty skewed, with the skew actually being described as where the tail goes. The tail is out to the right. Okay, so if you graph this very differently, like the one in the book, in simply 4 columns, this adds up to $100,000 plus and only 4 other columns below, you might think that those are fairly even. But if you stack it up in much finer bars, you see that, of course, it's not that even. The median household income is about $51,000. That is simply the midpoint. If you took away one household at the bottom and one household at the top and work your way into the middle, it's that center point. It's that center of gravity of this whole big distribution. Okay, the top 25%, lower 25%, etc., matching essentially what you see when you do a box plot around these. And you've already seen box plots. Okay. So that's a probability distribution. It's the percentage of a population, and if you randomly sample from the population again, the probabilities would be according to this shape on what kind of outcome that sample would have. So I throw a dart at the map of Orlando, or well, I should do this nationally, shouldn't I? So this is the U.S. Census. I throw a dart at the U.S. Census and I zero into the GPS point and I find the household that is closest to that dart, and I walk in to that house with a census clipboard and I ask them, what's your household income? The chances are highest that the people in that household would be in these general categories right down here, and relatively lower probabilities that folks would be in these kinds of outcomes here. Notice I'm talking about throwing a dart at the map. I'm talking about a random sample of this population would have these probabilities. Okay? So what do we mean when we talk about a conditional probability, where a probability depends on another probability? Well, a fairly straightforward data set in the text that describes this are the students who were sampled in the 70s smoking pot, and yes, I think of undergraduates as looking like this because I'm getting to be an old man, where the students' drug use here was specific to smoking pot, and it depended on parents' drug use, and that was broad categories. Drinking in the 70s, I'm assuming cocaine was involved, as well as pot there too, okay, and who knows what else. Okay, so the probabilities then in this table, which is called a contingency table, because the students' drug uses are contingent upon the parents, right? That's a contingency table. The probabilities for students then depend on another set of probabilities, their parents' drug use, okay? So this study was used to try to evaluate parental influences on their college-age students. It was college-age students because that's what psychology classes do to people. We census lots of young people in college classes because you have to enroll in a psychology class. So there's different kinds of probabilities we should talk about in here. One of them is the marginal probabilities. They are the probabilities at the margins of the table, right? 219 and 226 fairly balanced probabilities that students use or do not use pot in that sample, okay? Same sort of thing for the columns. 210 and 235, almost even numbers of parents that had used some sort of drug or alcohol, okay? Those marginal probabilities don't really tell the whole story, do they? You need to look inside the table at what are called the joint probabilities, those probabilities where you really do see the conditional differences of the outcomes. So the probabilities that students would be using because parents use seems to be higher than if they don't, and the opposite corner also seems to be higher. The probabilities that they don't is also appearing to be a little higher if the parents also do not, right? So that higher numbers in the corners can be represented, again, this way, but the calculations might vary depending on how you're expressing these. So these numbers in here are the percentages of the total. 125 out of 445 is 0.28, 28%. Okay? You want to express that differently if you wanted to know what are the probabilities that students use if parents also use, things like that. So let's talk about that a little bit closer. You might examine them this way. This is a Venn diagram, although it's a square one. You also might draw them as ellipses, where parents used is a certain percentage, students use is a different percentage, and those two numbers are then whether they match what the students using or not, and then neither, 0.32, would be this proportion where students do not and their parents do not as well. Okay. Now, if we wanted to consider this a little bit more closely, we might ask, for example, what is the probability the student who smokes pot has at least one parent who used drugs? So what we're asking then is this row. The student who smokes pot has at least one parent who also did some sort of drug or alcohol. That's a conditional probability. The probability of A given B is simply the probability of A and B divided by the probability of B. That's a simple way of calculating this, okay? So if we look at that, we have 125. Let me go back to the equation again. Sorry, I didn't mean to jump. The probability of A and B divided by the probability of B, right? So the probability of A and B is 125, and the probability of B is the 219. The probability of B is all those students who use things, okay? So we have 125 divided by 219.571, where the probability of a student that's yes, given the parent says yes, is this number, 125 divided by the 219. So over one half of the students who smoked pot had parents who did drugs as well. I can speak. Maybe I should not have done drugs. So what we have here then is this proportion of students using drugs depending on the parents' use or not, right? Okay, so we also have students who do not, and that 141 out of the 226 is the 0.62, right? So again, over one half, and slightly higher proportion, in fact. So those proportions that I just described are a little bit different than the ones here because it depends on the general question you're asking. Let me show you another example. I think this is a particularly useful one because it's nicely illustrated in the text by this tree diagram. It's just branching decision tree kind of numbers. This would be a study that was conducted in Canada where about 0.35%, or fortunately a small proportion of the women over 40, were diagnosed with breast cancer each year. Okay, that 0.35% is a small enough fraction that you might think we're not talking about a serious outcome, and that 0.35% comes from right here. These women were diagnosed with cancer. So if we start with that and work our way down, you might also see that in some cases a woman had cancer, truly did, and was tested positive. That's the proper medical diagnosis. But in some cases they had it and it was missed. That would be unfortunate. In other cases, they did not have cancer, but it was diagnosed as having it, and we don't want those outcomes either. And then these might be the ones that we would also be the relief, right? Not having it, not being diagnosed with it. What we don't want are the false positives, and we also don't want the false negatives. We do want to be able to diagnose it correctly or diagnose the absence of it correctly. Okay, so all of these probabilities are, if you look at this tree, are as if we are flowing from knowing the truth and working our way down through the test to calculate the probabilities of each of those alternative outcomes, right? In reality, of course, we don't actually know that information. It's not actually flowing downstream this way, where we already have a truth and then evaluate that with a diagnosis. We don't necessarily know that this 89% is that good an indicator, because guess what? If you take 0.0035 times 0.89, those two probabilities, it's actually quite a small proportion of, or I should say small probability of having that diagnosis. It's a much higher probability of not having cancer and having this negative diagnosis. Most women, fortunately, have that, okay? So if we're working this way, we're starting with this idea that we can diagnose the downstream, and we want to try to minimize these. So it would be useful to actually try to evaluate this in the opposite direction, because what we really do is start with the mammogram and then work backwards in the doctor's offices. And that's exactly what Bayesian theory is all about. We're just going to introduce that here. You're going to see a lot more Bayesian theory in the next course, but it's actually used very commonly, and you'll see why in just a moment. But it's also a big part of phylogenies. If you see an evolutionary tree with the probabilities at the nodes, the forking branch parts on a phylogenetic tree, those often high probabilities are calculated with Bayesian theory. So we have to remember that we're starting on the tips of the branches of one of those trees and working our way back up to try to calculate what the actual probability might be. So let's talk about how this would work. Bayesian theory says the probability that a patient has breast cancer given a positive mammogram test, that's this flow backwards here, all right, starting with the mammogram working back upwards, is the probability that there's breast cancer and positive mammogram divided by the probability of a positive mammogram, okay? So this Bayesian theory simply says we would work backwards in these calculations, where we start with this probability that they have breast cancer and positive mammogram, and then divided by the probability of a positive test, which is, remember, 0.89, I'm sorry, wrong one, this one, 0.06976 plus the 0.00312, okay? The probability of a positive mammogram test, that's the positives here and the positives here, both of those. So it turns out that that's a pretty small number there, right? 0.04 or 4% probability that having a positive mammogram result indicates truly a cancer result. That should tell you that if you're a doctor, you don't really want to rely too heavily on a mammogram positive result, right? That's why we have many follow-up tests for many kinds of initial diagnoses. A mammogram is really just a screening tool because this is actually a relatively low value when you think about these numbers, and you would want to follow up and see what are the chances that this positive diagnosis is in fact correct. A higher number, you hope, following up and more careful diagnostic tests. Okay? So Bayesian theory is a way to work backwards to try to identify the chances of a truth, as opposed to what you might start with that branching diagram where we presume we already know the truth and work out. Okay? Because what we really have are those end results. Okay, so if we're sampling and we're trying to calculate what these probabilities are, we have to think about how we collect those data, how we sample. So sampling might be thought of as with and without replacement. If you were to sample without replacement, it's essentially like a teacher picking kids out of a classroom, 1 out of 15. And if you just start with that, your chance of not being picked is pretty good. If you sit there quietly, don't raise your hand, and she doesn't notice that and pick on you just because of that, you have a pretty high chance of not being selected for some sort of question, right? 93% chance. But now let's say she's going to pick 3 kids, and they all go up to the board to draw something on the board, solve some math problem, something, okay? So she's going to pick you and 2 others. What are the chances you're going to end up sitting in the classroom and missing it, right? How much can you duck this job? Well, first she picks 1. So your odds of not being picked are 14 out of 15. Then there's 14 left in the classroom. She picks another one, that leaves 13, etc., right? So you multiply those three things together, you get 80% chance of not being selected to be one of the 3 kids at the board. That's sampling without replacement. Those 3 kids are removed from the pool each time she's trying to pick another kid, okay? As if those names were randomly drawn and then not putting back into the list of the kids still sitting in the chairs. Those sample events are not independent, right? Because each time you're changing the odds. It's no longer a sampling event that is independent of the next sampling event or the previous one. Flip that. If we're talking about sampling with replacement, same beginning, 93% chance of not being picked. But if she picks 3 in a row, and every time she does this, she's just as likely to pick you again. So it's truly like pulling balls out of the lotto bucket or names out of a hat, something like that, and putting the names back in to be picked once more. Now you've got an even chance every time, and it's a slightly higher chance you won't be picked. Why is that? Let me go back. If you think about, by the time it gets down to just you and one other kid in the classroom, it's a 50-50 chance. So this odds of being picked are going to eventually keep, these are the odds of not being picked, right? The odds of not being selected are going to keep decreasing the more and more kids get sampled to go up to the board. Here, the odds stay constant. So every time that she's selecting kids, it's a constant proportion, and those just multiply and stay higher. So if you're sampling with replacement, when the names are randomly drawn and put it back in the list, you maintain the constant probability, and each of those sampling events is independent, right? Because it's assuming it's a random shuffle. So with replacement is like adding a number back into the jar every time you reach in and take one out, and increases the odds that it too will be selected the next time. Okay? So how you collect your samples and how you count things in those samples will matter. If you're counting lots of cells or lots of organisms or lots of fruit flies or something in samples, you want to think about whether you're doing that with and without replacement, because that changes your counts and changes the probabilities of detection for certain kinds of outcomes, right? Okay, so let's get around to random variables, because we're talking about sampling many different kinds of outcomes. We start to think about these outcomes as whether or not they're truly random. So this applies best when you have numerical outcomes, as opposed to a binary or a limited set categorical like dice, where we have many possible numbers between some great big range, 0 and 100, and many possible decimal values in between that. I'm going to make one up here. Let's assume we're talking about dollars spent on beer per month per student, right? There's lots of different possible dollar amounts in that range among, say, 60,000 students at UCF. So each specific outcome, x, has a certain probability. That expected value of x, this e of x, is this x probability, our lowercase specific outcome, times the probability of that occurring, plus the next value times its probability, plus the next value times its probability, etc. Okay? So these probabilities are simply the proportion of students that spent that much on beer. So if I said there's no beer consumed, my x1 is no beer, and the proportion of students who spent no money on any beer in the course of a month, I'm assuming that's a fairly small number, times that 0 would tell me what I have for that probability, okay? And if I said plus 1 penny, plus 2 pennies, etc., all the way up, right? Okay, maybe we should do this in dollars, because I don't know if I can buy a beer for a penny. So we end up with these long series of very fine steps in our histogram, and if you were to consider that, we get a very smooth histogram that might be of some sort of shape. So, in fact, I looked it up. The average student spends about $50 a month on beer. So here, the mu is somewhere in the center of this distribution. Let's assume that's a 50, okay? And in this kind of a distribution, it says most students don't spend that much. There's a few out here who are spending a lot of time in the drunk tank, and there's a whole bunch of students who are controlling themselves. The mean is actually slightly above that peak. This is because it's a skewed distribution again. So the average that we're talking about in this distribution is really the center of gravity of this. If you were to balance that, it would be perfectly balanced on top of that average. Well, obviously just saying 50 doesn't describe a distribution like that very well. There's a lot of variation around that left and right, and you need to try to express that as well. And that's what variance is all about. A basic measure of the spread is a variance, and it's described as a square. I'll explain why in just a moment. You can also describe the variance as its square root, just simply standard deviation or sigma, okay? So it's squared because we take the differences from a value from the mean and square it, and we multiply it times that probability. And we do that for each probability all the way out until we get to our maximum value. We add those all up, and their product of those differences, the value from its mean squared times its probability. We add all those up. It's like called a sum of squares, essentially. And that can be very useful for expressing the variance. And essentially, if you have a mean and a variance, you're talking about some sort of normal distribution around a mean. All right, now, at least it can be used to describe that. It depends on the proportion of the means and the variances. Now, another way to describe the variance you've already seen would be the box plots. This would be a median, no longer a mean, but the spread around that box plot is another way to describe the variance. We typically assume a mean and a variance and standard deviations, etc. for normal distributions. They can be rather different from that. That's what the box plot is convenient for. You might see this median as being packed way down low or packed way up high in a distribution. That would be describing some skew, where the whiskers go way off to one side or way off to the other. Box plots represent the median plus 25% and minus 25%. So those are the quartiles, the 25, the 50, and the 75% quartiles. The whiskers on almost every software I can think of represent the 90% or the 10% minimum and maximum limits, okay? There's really no assumptions about normality if we're talking about a box plot, whereas if we're talking about a normal distribution, we're talking about a mean, for example, at 0, where it's very balanced to the left and very balanced to the right. It's a perfectly even bell curve, right? It's not skewed. Okay, so if we want to talk about random variables, the next thing we can get to, because we're talking about a very smooth distribution with lots of fine little tiny steps in our histogram, would be a continuous distribution, and we're stepping up towards histograms then. Now, the whole point of having many fine steps is that clearly this is kind of a crude approximation of a nice smooth distribution. If I had many more data and I could describe this in more smooth steps, I end up with something more like this. And you might say, well, it's almost like a bell curve, and so is this, but you could also say so is this. The problem is that it's harder to test and say that that's a really fine bell curve if you have relatively few points. It's much easier to say whether or not if it's a bell curve if you have many more points. So a continuous distribution assumes many fine steps. I'm not just measuring things in tenths in height. I'm measuring things in maybe individual centimeters or tenths of centimeters, okay? If I have finer gradations, I'm better able to describe a fine histogram. This is actual distribution of probabilities, on the probability distribution I can speak, of heights for US adults, okay? So this is setting up the next chapter. We're going to be dealing with how to measure distributions, how to assess whether it truly is normal Is there a lot of skew to it? And in fact, then we'll mess around with how to transform data sets to try to make them more normal, because the statistics we're doing this semester will assume a normal distribution. This is kind of close, although it's got some of that wiggle there, right? It's not that perfectly normal. There's sort of a funny bump going on out there. All right, well, so what have we gotten to here? The probabilities, really just the likelihood of a specific outcome, typically assuming you have lots of random samples, and you can describe that well. We're talking about outcomes that are either mutually exclusive or independent, depending on whether or not the probabilities depend on another one, a conditional probability, in other words. You have probability distributions, which are counts in many bins, hopefully many, and hopefully with lots of n in each bin, so you have a pretty good estimate. The independent samples are unrelated, but you could have conditional probabilities of different samples, and then that changes the odds, where it's not just simply a simple calculation. Sampling with and without replacement will change those odds. You need to think about how you're going to sample if you're going to be calculating some of these probabilities. Random variables are most smooth and most finely integrated when they're numeric, as opposed to tosses of a coin and rolls of a dice, which are categorical, or I should say binary, for the coin. And what we really generate in the end are histograms of many possible steps, if you have a random variable, that can build towards a continuous distribution that we can approximate with statistics, or see if our data can actually approximate it well or not. We hope well. Okay, so hopefully you're beyond what our chef is saying here, where he figured out that if he just makes if he makes an omelet with 3 eggs, he avoids giving people salmonella. I hope you all understand that probabilities are not quite that silly, and they're going to be important to a lot of our statistics. Okay, I think I've fumbled through enough of this, and I better stop now. And I think this one should be legible and audible, and we'll find out, since the previous one seemed to have a hiccup. All right, talk to you later. Bye.